Welcome to The Explainer. Today, we're tackling a seriously fascinating challenge from the world of electrical engineering. We're going to look at exactly how industrial electrical systems can transform power, literally shifting their physical configuration entirely without losing their underlying energetic meaning. I know, it might sound a little like magic, but I promise you, it's just pure, elegant mathematics.
Okay, let's dive into this blueprint. Now, I know what you might be thinking. At first glance, this handwritten source document looks, well, a bit intimidating, right? It's totally packed with Greek letters, square roots, and hardcore electrical jargon. But don't worry about that at all. We are going to decode this step by step together. By the time we finish, you'll see this not as a chaotic wall of equations, but as a beautiful, entirely logical story of energy transformation.
So, here is our game plan for today. First, the three-phase power puzzle. Second, finding equivalent resistance. Third, translating the voltage. Fourth, solving for the currents. And finally, unlocking total power output.
All right, let's kick things off with part 1, the three-phase power puzzle.
This is where we establish the fundamental problem we're actually trying to solve. Imagine having an electrical load shaped one way, but you urgently need to rebuild it into another shape entirely. Think of this process kind of like translating a classic book into another language. The star connection, which literally looks like a Y with a central neutral point, is our starting language. The delta connection, which forms a closed loop like a triangle, is our target language. And this brilliantly illustrates our core challenge. The actual meaning of the electrical power has to remain identical, but the words, the structural shape, and the individual component values must completely change to adapt to this new closed-loop geometry.
Every good puzzle starts with a few known pieces, right? Well, our source document gives us these starting variables to work with. We've got a balanced star phase resistance of 12 ohms, a hefty line voltage of 415 volts, and a perfectly clean power factor of 1. These specific numbers are the raw materials for our entire mathematical metamorphosis. Keep them in the back of your mind because they basically dictate everything that follows.
These variables basically give us our conversion roadmap. Let's move to and see how this builds, because we have 4 distinct mathematical checkpoints to hit: equivalent resistance, phase voltage, currents, and finally, total power.
Moving right along to part 2, finding equivalent resistance.
So, this brings us to our first major mathematical hurdle. How exactly does resistance scale when the very shape of the circuit shifts from a branching Y to a closed triangle? It turns out that the math behind this is surprisingly elegant. For a balanced system like the one we're looking at, the star-to-delta conversion rule is incredibly simple. The resistance in the delta configuration is exactly 3 times the resistance in the star configuration. It's just a direct proportional leap.
So we take that starting 12 ohm star resistance, multiply it by our conversion factor of 3, and boom! We get an equivalent delta resistance of 36 ohms for each branch of our new triangle. Just like that, we've already solved the first piece of the puzzle.
Next up is part 3, translating the voltage.
With the resistance sorted out, we step into the next phase. Now, if resistance is the obstacle to the flow, voltage is the pressure actually pushing the electricity through. We need to see how this pressure behaves in our new delta shape. And here is a fundamental rule of electrical geometry. In a delta connection, the voltage across any single phase, meaning one side of our triangle, is exactly the same as the voltage across the main supply lines coming in from the power grid. There's no drop, there's no reduction, they are literally one and the same.
Because our original problem clearly states that the line voltage is 415 volts, our delta phase voltage locks in right there at that exact same powerful 415 volts. No complex math required for this step, just a really solid understanding of how the delta configuration distributes pressure.
All right, part 4, solving for the currents. We've got our resistance and we've got our voltage. This means we can finally calculate the actual flow of the electricity. But in three-phase systems, current isn't just one simple number. We have to be very careful with our definitions. Now, what's really interesting about this slide is the concept of phase current. Imagine that delta triangle in your head. The phase current is the localized, specific flow of electricity traveling through just one individual branch or resistor of that closed loop. It is strictly the inner circulation of the system. To actually find it, we rely on good old Ohm's law. Current equals voltage divided by resistance. We just take our phase voltage of 415 volts and divide it by our newly calculated delta resistance of 36 ohms.
And that calculation gives us 11.53 amps. That is a solid, substantial amount of current flowing through each individual coil of our delta load. But remember, we're still just talking about the inner loop here.
We absolutely must contrast that inner flow with the line current. Think of this as the heavier combined electrical flow rushing from the main power source, traveling down those main supply conductors before it hits our load and splits into the delta loop. It is the grand total flow that's feeding the beast.
In a delta system, the relationship between that inner phase current and the incoming line current involves a very specific, almost magical constant, the square root of 3. The line current is exactly the square root of 3 times larger than the phase current. So we multiply 1.732 by our 11.53 amps. And that reveals a near-perfect 19.97 amps, which the source neatly rounds up to exactly 20 amps. Notice how elegantly the mathematics scale the current up here. Those main feed lines have to carry significantly more current than any single branch inside the delta loop, simply because they're supplying the entire system.
Finally, we arrive at Part 5, Unlocking Total Power Output.
We've reached the summit, folks. This is where all these individual metrics, the resistance, the voltage, those shifting currents we just found, finally combine to perform actual real-world work. We bring all our hard-won variables together into the master three-phase power formula. Total power equals the square root of 3 times the line voltage times the line current times the power factor. So we plug in our 1.732 times our 415 volts times our almost 20 amps and multiply it all by 1, since our source kindly gave us a perfect power factor.
So the crucial point is the final result, 14,358 watts, which naturally translates to 14.36 kilowatts. And this isn't just abstract math on a whiteboard. 14.36 kilowatts is serious, tangible energy. To put that into perspective for you, that is enough continuous electrical power to run several large central air conditioning units all at the exact same time.
Let's just take a quick step back and look at this beautifully clean summary table. We successfully decoded the entire metamorphosis. We took a simple 12-ohm star configuration, completely reshaped it into a delta, mathematically predicted how the resistance would triple to 36 ohms, tracked the exact phase and line currents at over 11 and almost 20 amps respectively, and finally proved that it all results in a massive 14.36 kilowatts of power.
We started with a pretty intimidating page of raw formulas, but by just applying clear, structured logic, we revealed the dynamic, breathing electrical system underneath. It really makes you wonder, doesn't it? If translating a system from star to delta can completely alter its internal physical dynamics while seamlessly maintaining its total power, what other incredible industrial mysteries are hiding in plain sight, just waiting to be unlocked by basic algebra? Keep exploring, keep questioning, and I'll see you in the next explainer.